This is a demonstration of EFilter, a tool for identifying spurious or suspicious tax IDs in metagenomics datasets. The goal of this video tutorial is to show EFilter in use. For details about EFilter construction, please see our accompanying paper. The first step is to upload your data. Data should be in the form of text files. Specifically, you want to upload lists of taxa from your metagenomics samples. These lists can be tax IDs or Latin names, and Latin names can be at any taxonomic rank. In fact, you can upload lists of mixed rank. So for instance, you can upload lists that include families, genera, and species. EFilter automatically assigns taxonomic rank to tax IDs or Latin names. Here's an example of input files with species name. In general, we've tried to make EFilter as user-friendly as possible, which means that you can run EFilter on a point-and-click basis. The first choice that you need to make is whether to analyze your files separately or as a single pool. The default is to pool files, but I'll choose to analyze them individually because it provides a little bit more information. To do that, I'm going to click on the Individually Radio button. The next step is to upload files. To do this, you double-click on the Browse button. You then navigate to the folder with your text files and select all of the files that you want to analyze. Notice that EFilter can analyze files in batch. So for example, I've just uploaded a total of 15 files. The first thing that happens after you upload your files is that EFilter tells you how many distinct taxa it has found and at what taxonomic ranks. It also tells you how many taxa were not in the EFilter database. These could be bacteria that are not well defined, bacteria that were defined after the most recent EFilter update, or even taxa that are not bacteria at all. For example, they might be fungi or archaea. EFilter will ignore all taxa that it does not find in its database, so you do not need to manually curate shotgun sequencing data that might have non-bacterial organisms. EFilter presents information about taxon counts both for each individual file and for all files merged together. The next thing that you'll find is a list of all of the taxa, along with the known habitats for each. So for instance, for Abiotrophia defectiva, we don't have any recorded habitats. However, for Acinetobacter johnsoni, we have this taxon recorded from a variety of habitats, including birds, humans, food, and waste. Habitat information is presented for the input taxonomic rank and also for higher taxonomic ranks. Here, for example, we see habitat information for genus level and for family level for our list of species. Not surprisingly, habitat coverage for species is somewhat spotty. It becomes much more complete for genera and for higher taxonomic ranks. The next step is to define your filter. To do this, point and click on the Define Filter tab. Depending on your goal, it's generally advisable to start with broad filters. So for instance, if you have human skin samples, you might want to consider a filter that includes all body sites, humans, and mammals. Habitats can be combined in any logical combination. To do this, click on all of the habitats that you want to include, and then add these environments by clicking the Add Selected Environments to Target button. This adds the habitats to the filter, but does not specify their logical combinations. To specify logical combinations, click on the habitats you want to combine. Here, for example, I want to combine all the habitats with OR. So, once I've selected all the habitats, I'll click the OR button. This creates a new filter with the chosen habitat combination. To use this filter, click on it. Then click the Filter Database button. For each file, EFilter then outputs the total number of taxa that passed, the number that failed, and the number whose names were missing. Passing means that the habitats selected in the filter are known habitats for those taxa. Passing and failing information is presented both as counts and in graphical form. If you want to know which organisms passed or failed the filter and at what taxonomic rank the failure occurred, you can click on the Match Higher Levels tab. This breaks down passing and failing taxa by file and by taxonomic rank. For large systems or multiple inputted files, this table will be very large, but you can quickly navigate the table by sorting each column. So for instance, if I want to know where the egregious failures are, I can sort by a high taxonomic rank, for example, family. These particular taxa are ones that I want to examine carefully since they represent highly likely issues with sequencing or bioinformatics pipelines. The final functionality provided by EFilter is to suggest taxa that match a particular filter at taxonomic ranks equal to or lower than the inputted rank. Since the example I've just used inputted taxa at the species level, I'm going to upload a different dataset with only genus names. This time, you see that we have only genera. For the sake of example, I'm also going to pick a slightly different and more complicated filter. Let's suppose I want any human body site or human habitat, but I do not want any taxa found on vultures or birds of prey. Because vultures is not a predefined habitat, you have to create a new filter for it. For any single word that you want to use as a habitat, click on the Define Filter tab and then click on the Keywords in Text tab. Then type in your word of choice. I'll type vulture. I'm then automatically provided with a list of words containing my keyword. I'll select both vulture and vultures and add them to my list of habitats. For any phrase that you want to use as a habitat, click on the User-Defined Phrase tab. Then type in your phrase of choice. Here I'll type birds of prey. In this case, I'm provided with any instances of that phrase in the database. If the use of the phrase looks appropriate, I can add the phrase to my list of habitats as well. Okay, now for creating the appropriate logical combination of habitats. First, I select the habitats I want to combine with OR. I've already done that for the human habitats, so I'll continue to use that particular logical combination. Then I select vulture, vultures, and birds of prey, and I also combine them with OR. Again, this adds the OR combination of vulture, vultures, or birds of prey to my list of filters. Now I want to combine the human habitats and the vulture and birds of prey habitats using NOT. So I click on the two sets of OR combinations and then I click NOT. I clicked on the humans, I clicked on the vultures and birds of prey, and then I click on NOT. Notice that when combining with NOT, habitats are linked in the order that they are clicked on. So if I had clicked on vulture habitats first, I would have created the filter vultures and birds of prey, not human. Whereas by clicking on the human habitats first, I create the filter human, not vultures and birds of prey. All right, now I'm going to apply the combination filter to my genus level dataset. Again, I do that by clicking on the particular filter I want and clicking the Filter Database button. As before, I get out a list of passing and failing taxa. Moving on, I want to show how EFilter can predict organisms at lower taxonomic ranks that match the selected filter. In particular, if you click on the Match Lower Levels tab, you are provided with lists of species that pass the filter even though I inputted genera. So here's my list of species, and here's the input genus. This functionality is useful if you're using sequencing, for example 16S, that can only provide taxonomic identification at a higher rank, but you want an educated guess as to what organisms might be present at lower ranks. All right, so that's a demonstration of EFilter usage. The final step is outputting your data. For this, navigate back to the Match Input Level tab, and you will see an Export All Results button. Click on this, then click OK to accept the download. If you navigate to your Downloads folder, you should see a zip file with the output. Within this zip file, you should find CSV files with all the relevant outputted data, as well as PNG files with the graphical presentation of passing and failing taxa. So there's my list of CSV files, and there's the PNG file. And I can open this up. There you go. There's the picture. And we will just open up one of the CSV files. And there you go. Hopefully this demonstration has been useful and has answered many of your questions on EFilter usage. If you have additional questions, I'd encourage you to reach out to us and we will help you through the analysis of your data.